In this session we're going to do a sample problem in the framework of waiting cost analysis, trying to minimize the cost of providing service and the cost of customer waiting. From our lecture, we know that we can express this cost as the sum of the hourly cost of providing service times the number of servers we provide, plus the hourly cost of customer waiting, plus the number of customers who are waiting. We're seeking that expression is the expression for this curve. We're seeking the minimum point on that curve. We're going to find that through a table we'll construct for various values of S. Here's our sample problem. Trucks arrive at a warehouse at a rate of 11 per hour during business hours. A single crew can unload trucks at a rate of 4 per hour. Each crew requires its own loading dock at which to work. There are 7 unloading docks at the warehouse, although an extra dock could be built for an estimated $50,000. An unloading crew, 2 workers and a forklift, cost $75 per hour. The truck and driver cost $275 per hour. Assume trucks queue and wait for the next available dock. How many crews should be hired? Assume plus on arrivals and exponential service rates. If you need to build a dock, amortize the cost of the dock over 10 years or 20,000 working hours. Now, because we've made this assumption, assume trucks wait and queue for the next available dock, we can treat this as a multi-server problem, right? A multi-channel problem. And because we've made this assumption, plus on arrivals and exponential service rates, we can use the table that I've provided you that gives the value of LQ, the number of customers waiting, for various servers in a system with various numbers of servers for a system with plus on arrivals and exponential service rates. That table is here, and what it's going to require us, the parameters it requires for us to use it, are the number of servers, that's what's in the columns here, the number of servers, and the number of customers being served, the number of customers in service, lambda divided by mu. So what we need to know from our problem to be able to use this table is S, lambda, and mu. And when we know S, lambda, and mu combined, we can look up in this table the value of LQ. Alright, so let's start a new spreadsheet here and try and capture some of the data that the problem statement gave us. Let's go back to the problem statement. We know trucks arrive at the warehouse at a rate of 11 per hour. That arrival rate is lambda. And a single crew can unload trucks at a rate of 4 per hour. That service rate is mu. So let's get both of those recorded in our sample spreadsheet. We have lambda is 11, and mu is 4, which means the number in service is going to be 2.75. Just make this a little bigger. See it a little better. Alright, we'll get back to the problem and we'll see what else we can pull out of the problem statement. There are 7 unloading docks at the warehouse, although an extra dock could be built for an estimated $50,000. Now, the way we're going to proceed with that is we're going to hope that our answer is to hire fewer than 7 crews, and we're not going to have to build that dock. If that's not true, we'll come back to that. An unloading crew and forklift cost $75 per hour. The truck and driver cost $275 per hour. Now those are the parameters we have here. K1, cost of a server, that's going to be $75 per hour. K2, cost of customer waiting, that's going to be $275 per hour. So let's get those recorded into our spreadsheet. K1, $75 per hour. K2, $275 per hour. Alright, now let's just peek and see if there's anything else we need from our problem statement. Trucks queue and wait for the next available dock. That's what let us use the table. And the question is how many crews should be hired. So S, the third parameter we need to solve our queuing problem, is actually the decision variable. And we're going to search over S to find the minimum cost. Right? Again, what we're doing is we're varying S, we're changing S, and searching on this total cost curve for the lowest cost we can obtain. What we'll do is we'll start with the smallest value of S that works, the smallest value of S that gives us a utilization less than 100%, and then we'll keep incrementing S. We'll keep incrementing S until the total cost begins to increase. If at any point we reach the stage where the total cost begins to increase, we know we can stop, because once the cost begins to increase, it continues to increase. Right, to find that point, we search over values of S and we build this table. So we have a table that gives us various values of S, and then the cost of providing service. Then we have the number of customers who will be waiting in line, the average number of customers who will be waiting in line if we hire S servers, and the cost of customer waiting. Then we'll sum those two to find out what the total cost, the total average waiting cost would be if we hire S servers. All right, where can we start with S? Well, clearly we can't hire just 2 people because we have 2.75 people being served. If we have 2.75 people being served, we must hire at least 3 servers, right? If we hire 3 servers, how much is that going to cost us? Well, each server we hire costs us $75, right? And we have to multiply that by the number of servers. How many people will be in line if we hire 3 servers? Well, the data we have now is 3 servers and 2.75 being served. Let's go try to find that in our spreadsheet. What we see as we go through here, we have the column for 3 people being served, column C, but we don't have the row for 2.75 customers in service. But recall that in this table, all we need to do is type in the value we want, 2.75, and the formulas adjust automatically. So now these are the values. These are the values for how many people will be in line. If we hire 3 servers, we'll have 9.31 customers in line. 4 servers will have 0.9 customers in line. And note, this is what we mean when we say that the waiting cost function is a nonlinear function. Going from 3 to 4 servers, we've increased capacity by 33%. But going from 3 to 4 servers, we've reduced the number of customers waiting 9-fold, from a little over 9 to a little less than 1. Right? So 4 servers, if we hire 4 servers, there'll be 0.9 customers in line. 5 servers, there'll be 0.22, etc. What I suggest we do here is just go ahead and copy these values. We'll copy just the values themselves, not the formulas, and paste them into our table so that as we go through, we don't have to continue to refer to this table. So we'll copy it and then go over to our spreadsheet and paste them in. But now, of course, we don't want to just paste them in lengthwise. We'll have to do paste special and transpose those values. So paste special. And what I want are just the values, and I want them transposed so they have them in a column instead of a row. And there they are. Alright, so if we have 9.31 customers being waiting in line, how much does that cost us? 9.31 customers at any point in time are in line on average. Well, that costs us $275 per customer times the number of customers who are in line. And let's go ahead and format these as dollars because that's what they are. The total cost will be equal to the sum of those two. The total cost if we hire 3 servers, the total cost of waiting will be $2,786.24. Alright, what if we hire 4 servers? Well, if we hire 4 servers, the cost of service, 4 times 75, is going to be $300. If we hire 4 servers, we've already seen we only have 0.9 customers in line. If we only have 0.9 customers in line, $275 times 0.9 customers, that's going to cost us $247 in customer waiting cost. So $300 in service providing cost, $247 in customer wait cost, means the total cost of waiting is going to be $547. Alright, our costs are still going down, so we continue to search. What if we hire 5 servers? Well, then in that case, Our service provision cost will be $375. We've hired another server. The number of customers waiting will go from 0.9 down to 0.21. That's 0.21 times $275 means our waiting cost is going to go down to $60. And our total cost, $375 plus 60, is going to continue to go down. Now we only pay $435. That's the total cost of waiting. All right, our costs are still going down. Let's see what happens when we provide 6 servers. When we hire 6 crews to unload the trucks, then the cost of providing service is going to go up to $450. $75 per crew times 6 crews, $450. Now we're actually done, right? Because $450, the cost of providing service is now greater than the total cost we've already calculated. But just to verify, let's continue. So we have the cost of the number of customers waiting drops down to about 0.06. Only 0.06 customers waiting on average at any point in time. That costs us about $16 for customer waiting, and the total cost of the system is now $450 plus $1633. The total cost of the system has risen now to $466, and sure enough, we're finished. Because we know if we continue, the cost will just continue to rise. So the optimal answer here is 5 servers, 5 crews should be hired in this case, and the cost of that will be $430. The total cost of waiting in that system will be $435. One final thing here, let me point out that with 3 servers, the cost of waiting greatly exceeded the cost of providing service. With 4 servers, the cost of providing service exceeded the cost of waiting. So if what we were seeking was the place where those 2 costs are equal, if what we were seeking was the place where the cost of providing service in the margin is equal to the cost of waiting, the right answer would either be 3 or 4, or if we could hire part-time, something in between. But the right answer here is not 3 or 4 or anything in between. The right answer here is to hire 5 servers. And the reason for this is because the cost of waiting is highly nonlinear. So the cost of waiting, as we move from 4 to 5 servers, is dropping more quickly than the cost of providing the service is rising. This is rising at a roughly linear rate, $75 for each server. This is dropping at a highly nonlinear rate. So that's why in this case we can do better by hiring more even when we're past the point where the 2 marginal costs are equal. I hope that's useful to you. We'll see you in the next problem.